Right now, light is hitting your eyes at 186,000 miles per second, and the particle carrying that light, the photon, has never aged a single second, ever. From the moment it was born to the moment it dies inside your eye, its clock reads 0. We are going to go inside that photon. We will watch time freeze, see the universe flatten into a single point, and find out why the oldest light in existence is still brand new. We will even break the math trying to describe it. If you enjoy the journey, like and subscribe. Let's go. Right now, without moving a muscle, you are being hit by light that has traveled longer than human civilization has existed. Every second, trillions of tiny particles slam into your skin, your eyes, the floor beneath your feet. You cannot feel them land. You cannot hear them arrive, but they are there, and they have been crossing the universe for longer than you can picture. These particles are called photons, and they carry something strange with them. Every single photon that touches you right now is frozen in time. Its internal clock reads 0. It has no age. The photon that left the sun 8 minutes ago and the photon that left a distant star 400 years ago share one identical quality. To each of them, no time has passed. None. Ever. Think about what that means for a second. The star you see on a clear night might already be dead. It burned out 1,000 years ago. The photon it fired is only reaching you now. But that photon experienced 0 seconds of travel. To it, the star that created it and your eye that absorbed it are the same single instant. The star's final explosion and your quiet backyard are, from the photon's perspective, touching. Scientists have confirmed this through experiments, through the math of Albert Einstein's theory of special relativity, and through atomic clocks flown on real airplanes. Time dilation, the slowing of time for fast-moving objects, is not a guess. It is measured, tested, and accurate enough that your phone's GPS system depends on it every single day to within a few feet. But here is the part that makes physicists pause. A photon does not just slow down in time. It stops completely. Not almost stops. Stops, frozen at absolute 0 on the timescale from the moment it is created to the moment it is destroyed. Every image you have ever seen entered your brain through particles that have never aged. Every memory built from light, every face you recognized, every sunrise you watched, all of it arrived on the backs of timeless messengers. You have spent your entire life receiving information from objects that exist outside of time. And the photon carries something else with it. Color. The color of everything you see is simply a measurement of how much energy each photon carries. A red photon carries less energy. A violet photon carries more. That difference in energy is the only reason red looks different from violet. The entire visual world, every shade, every tone, every hue you have ever experienced, comes down to the energy level of frozen, ageless particles. Now here is where it gets stranger. A photon born inside the core of the sun does not zip straight to your eyes. It gets trapped, bouncing off one atom, then another, for up to 100,000 years before it even reaches the sun's surface. 100,000 years of pinball inside a star. Then, the moment it escapes, it crosses 93 million miles of empty space and reaches Earth in 8 minutes and 20 seconds. 100,000 years stuck inside a star. 8 minutes to cross the solar system. 0 seconds experienced by the photon itself through any of it. Something about that should feel wrong. And that feeling is exactly right, because the universe operates by rules that make perfect sense in the math, and almost no sense to a human brain standing in a backyard looking up. The question is, what are those rules, and how did we find them? Before we go any further, we need to get one thing straight. A photon is not a tiny glowing ball floating through the air. Picture a ripple on a pond. Now picture that ripple being so precise, so tightly wound, that it acts like a single particle when you try to measure it. That is closer to what a photon is. It is a ripple in something physicists call the electromagnetic field, a field that fills all of space, everywhere, at all times. When something energetic happens, like an electron inside an atom dropping to a lower energy level, that field gets disturbed. The disturbance shoots outward. That disturbance is the photon. It carries energy. It has no mass. And those two facts together are what make it unlike anything else in the universe. Mass is the property that makes things resist movement. The heavier something is, the harder you have to push to get it moving. A bowling ball needs more force than a tennis ball. A car needs more than a bicycle. But a photon has zero mass, nothing to resist, nothing to overcome. So the moment it is created, it is already moving at the maximum possible speed the universe allows. It does not accelerate. It does not build up. One instant, it does not exist. The next instant, it is moving at 186,000 miles per second. And it never slows down. In a perfect vacuum, a photon travels at exactly that speed forever, until something absorbs it. A wall, a leaf, a human retina. The moment it hits something and gets absorbed, it is gone. It transfers its energy and ceases to exist as a photon. This is important. A photon does not have a long life where it slowly ages and eventually dies. It is born instantly at full speed and destroyed the moment it hits its target. In between, from its own perspective, there is nothing. No journey, no passage of time, no experience of moving through space. Now, the electromagnetic field that photons travel through is everywhere. It passes through walls, through your body, through the earth. Most photons pass right through without interacting with anything. The ones that do interact are the ones we can see or feel. Visible light, radio waves, microwaves, X-rays. All of them are photons. All of them are the same kind of particle, just carrying different amounts of energy. A radio wave photon carries very little energy. A gamma ray photon carries so much it can break apart the molecules inside your cells. Scientists figured out this unified picture in the 1800s. A physicist named James Clerk Maxwell showed that electricity and magnetism were two faces of the same force, and that light was a wave in that combined field. It took another 50 years and Einstein's work to show that this wave also behaves like a particle, depending on how you measure it. That puzzle, wave or particle, is still one of the strangest unsolved puzzles in all of science. And it matters for understanding the photon's relationship with time, because quantum mechanics and the theory of relativity describe the photon in completely different ways, and they do not fully agree. That disagreement is going to matter more than you might expect. But first, we need to understand the stage everything happens on. There is a speed limit carved into the fabric of reality itself, 186,000 miles per second. Nothing with mass can reach it. And unlike a speed limit on a highway, there is no way around it. But why? Where does this limit come from? Who set it? The answer starts with something you do every day without thinking about it. Moving. Everything in the universe is always moving. Even if you are sitting perfectly still in a chair, you are moving. Through time. Right now, you are aging, cells are dividing, clocks are ticking. And all of that counts as motion. Scientists call the four-dimensional structure you are moving through space-time. It combines the three dimensions of physical space, up-down, left-right, forward-back, with time as a fourth direction. Here is the rule that governs everything. Every object in the universe has a fixed total speed through space-time. You cannot increase it, you cannot decrease it. It is always the same. What you can do is change how that speed is divided between space and time. If you sit completely still, all of your motion goes into time. You age at the fastest rate you can. If you start moving through space, your motion splits between space and time. The faster you go through space, the slower you go through time. Time literally slows down for you. This has been measured. Clocks on fast-moving planes tick slower than clocks sitting on the ground. Scientists measured this in 1971 with atomic clocks and got exactly the result Einstein predicted 66 years earlier. Now push this to the extreme. If you could somehow reach the speed of light, all of your motion would pour entirely into space. Zero would remain for time. Your clock would stop completely. That is the speed limit. 186,000 miles per second is the exact rate at which all your motion capacity gets used up by moving through space, leaving nothing at all for time. A photon hits that limit perfectly. It moves through space at the maximum rate and through time at zero rate. Its clock is frozen permanently. For anything with mass, reaching that limit is impossible. And the reason why is one of the most dramatic facts in physics. As you accelerate something with mass, it gets heavier. The faster it goes, the harder it becomes to push it further. To get a single grain of sand, one tiny speck of dust, to the speed of light, you would need to keep adding energy forever. An infinite amount of energy. More than everything the sun will produce in its entire life. More than every star in every galaxy combined. The math says you would need infinite energy, and infinite energy does not exist in a finite universe. So the speed limit holds perfectly. Always. Einstein worked this out at age 26 while thinking about trains and beams of light. He published his theory of special relativity in 1905 and overturned centuries of assumptions about how the universe works. But there is one piece of his reasoning that almost nobody talks about, and it changes how you see everything. Einstein did not just say time slows down for fast objects. He said time is not a fixed thing at all. It is personal. Your time and my time are not the same if we are moving at different speeds. There is no universal clock ticking at the same rate for everyone. That idea alone cracked open a completely new picture of reality. And the stranger part is what it means for the experience of something with no mass at all. In 1905, a 26-year-old patent clerk in Switzerland changed everything we thought we knew about time. And he did it without a single lab experiment. Just his mind and a pencil. Albert Einstein sat with one question that everyone else had brushed past. What would you see if you could ride alongside a beam of light? Imagine you're on a train. The train moves at normal speed, and you throw a ball forward. To you, the ball moves at the speed you threw it. To someone watching from the side of the tracks, the ball moves at the speed of the train, plus the speed you threw it. That is just how speeds add up. Everyone agreed on this for centuries. Einstein asked, what if the ball were replaced by a beam of light? The train moves at half the speed of light. You point a flashlight forward. How fast does the light beam move to the person standing outside on the tracks? The old math said, the speed of light plus half the speed of light. But every experiment ever done showed that light always travels at exactly the same speed. It does not matter how fast you are moving. It does not matter which direction you fire it. The speed of light is always the same for every observer everywhere. That is impossible unless something else is changing. Einstein saw what that something was. If the speed of light must stay constant for everyone, then time itself must stretch and compress, depending on how fast the observer is moving. Time is doing the adjustment. The universe bends time to protect the speed of light. This is called time dilation. It sounds wild, but it is accurate enough to run the GPS system that tells your phone exactly where you are. The satellites orbiting Earth move at roughly 8,700 miles per hour. Because of that speed, their onboard atomic clocks tick slightly slower than clocks on the ground. Engineers apply a correction every single day. Without it, your GPS would drift by miles within hours. Einstein's 1905 paper also introduced the idea that space and time are not separate things. They are woven into a single fabric. Physicists call it space-time. And this fabric is not rigid. It flexes. It stretches. It curves around massive objects. The sun bends space-time around it, and Earth follows that curve, which is what we call gravity. Before Einstein, people believed in something called absolute time, a universal clock ticking at the same rate for everyone, everywhere. Newton built his entire picture of physics on it. Einstein showed that there is no such clock. Each observer carries their own time, and the rate at which it ticks depends on how fast they are moving and how strong the gravity around them is. For a photon, this means something almost impossible to accept. A photon moves at the maximum possible speed. Its time dilation is total. Its clock does not tick slow. It does not tick at all. Einstein himself struggled with what it meant to talk about a photon's experience. The math for calculating time from the photon's perspective produces a result that requires dividing by zero. The equation simply breaks. Physicists are still arguing about what that means for reality. But before we get to the breakdown of the math, there is something even stranger about what the photon experiences in space. Because time is not the only thing that changes at the speed of light. You have been living inside something your whole life and never noticed it. It has no color, no texture, no smell. You cannot touch it or point at it, but everything you have ever experienced, every moment you have lived, every object you have seen, exists inside of it. Physicists call it space-time. Before Einstein, scientists treated space and time as completely separate things. Space was the three-dimensional arena where events happened. Three directions, up and down, left and right, forward and back. Time was something else entirely, a separate river flowing forward at its own pace, independent of everything. Einstein fused them. He showed that space and time are not two separate things. They are two directions inside the same four-dimensional structure, the same fabric. You cannot change one without affecting the other. Speed through space slows time. Gravity bends both. Here is how to picture it. Lay a bedsheet flat in the air. That sheet represents space-time in two dimensions. Now place a bowling ball in the center. The sheet bends and dips around the ball. Objects rolling across the sheet follow the curve. They curve toward the bowling ball because the sheet is curved, not because some invisible hand is pulling them. That curve in the sheet is what gravity actually is. Einstein showed that massive objects like the sun, the earth, even you, bend the space-time fabric around them. Everything nearby follows that bend. This picture replaced Newton's idea of gravity as a force reaching across empty space. Einstein said there is no pull, there is only curvature, and matter tells space how to curve, while space tells matter how to move. Now take that picture and ask what happens to a photon. A photon follows the curves in space-time just like everything else. When light passes near a massive object, it bends. Astronomers proved this in 1919 when they photographed stars during a solar eclipse and saw the stars appear slightly shifted from their true positions. The sun's space-time curvature had bent the light coming from behind it. This is real, measurable, confirmed. But inside that fabric, something specific happens to the photon that nothing else experiences. Every object in the universe moves through space-time at a fixed total rate. For you, sitting still, almost all of that rate goes into moving forward through time. You age at the maximum possible speed. For a fast jet pilot, a little more motion goes into space and a tiny fraction less goes into time. The pilot ages just slightly slower than you, by a fraction of a millisecond per flight. For a photon, 100% of its motion is through space. 0 goes into time. The space-time fabric carries it at the maximum rate through three-dimensional space, while time contributes absolutely nothing. And here is the part that gets physically strange. As something moves faster through space in that fabric, the physical space ahead of it compresses. The universe squishes. Distances shrink. The faster you go, the shorter the distance you are crossing becomes. This is called length contraction, and it is as real as time dilation. For the photon, moving at the absolute limit, length contraction reaches its extreme. Space does not just shrink. Space collapses. And what is left after that collapse is something no human has ever truly seen. There is a rule every object in the universe follows, and almost no one talks about it. You have a fixed total speed. Always, every moment of your life, you are moving through the space-time fabric at the same unchanging rate. What changes is not your total speed. What changes is how that speed is divided between two directions: space and time. Right now, sitting still in your room, nearly all of your total space-time speed is going into time. You are rocketing through time at full rate. Your cells are aging. Your brain is changing. Your clock is ticking as fast as it can. You are barely moving through space, so almost everything you have goes to time. Now imagine you jump in a car and drive. A tiny slice of your total speed shifts from the time direction to the space direction. Your clock slows down by an amount so small you could never measure it in a car. But it slows. This is not a thought experiment. This is what happens. A jet fighter pilot moving at 1,000 miles per hour ages slightly slower than someone standing on the ground. The difference is a fraction of a nanosecond per flight. Still real. Atomic clocks sensitive enough to detect it have confirmed this multiple times. Now imagine a spacecraft moving at 90% of the speed of light. The trade-off becomes dramatic. A large chunk of total space-time speed is now devoted to moving through space. Time slows significantly. An astronaut on that ship ages slower by a factor that you could actually see. If they left Earth at age 20 and returned after what felt like 10 years to them, decades might have passed on Earth. This is not a movie plot. This is what Einstein's equations predict, and every precision experiment performed since 1905 has confirmed it. Now push the object to 100% of the speed of light. All of the total space-time speed pours into moving through space. Zero remains for time. The clock does not just slow, it stops. Completely. Permanently. A photon lives at that extreme. Every unit of its space-time motion goes into space. Time gets nothing. From the moment it is born to the moment it is destroyed, the photon's internal clock does not tick once. Here is why that should bother you. You experience time as a river, always flowing forward. You feel moments passing, but a photon that just hit your eye after traveling from a star 400 light-years away experienced that entire journey in the same way you experience the gap between two identical photographs. There is no gap. Both images are the same moment. The photon born at that star and the photon absorbed in your eye are not connected by a journey. They are the same event, collapsed together. Now think about this. If a particle of light can exist with no time passing, what does that say about time itself? Is time a real physical thing, or is it only something observers with mass experience? Physicists are still arguing about this. There is no clean answer, but the debate gets wilder when you look at what happens to space at the speed of light. Because time is not the only thing that freezes. A photon's clock stops completely. And we can show you exactly why step by step. Go back to the trade-off. Every object in space-time has a fixed total motion rate. Some goes to space, some goes to time. The faster you move through space, the less goes to time. A photon moves through space at the absolute maximum, leaving exactly zero for time. So the photon's clock ticks at zero. Its age never increases. Its internal state never changes. From its creation to its destruction, there is no before and no after. There is only the event of existing. Now here is what makes this physically real rather than just a math trick. Scientists proved it with muons. A muon is a particle similar to an electron but heavier. Muons form in the upper atmosphere, about 60 miles above your head, when cosmic rays hit air molecules. They are unstable. They fall apart in roughly 2 microseconds, 2 millionths of a second. At the speed they travel, around 98% of the speed of light. They should decay long before reaching the ground. The math says they should only make it about half a mile before dissolving. But they reach the ground in huge numbers. Every square foot of Earth's surface gets hit by muons constantly. How? Because time dilation is real. At 98% of the speed of light, the muon's clock runs so slow that its 2 microsecond lifetime from our perspective stretches into something much longer. The muon experiences its short life at its own slow time rate, but we see it lasting long enough to cross 60 miles of atmosphere. The muon does not know it survived longer than it should have. From its own perspective, it lived exactly as long as a muon lives. Space contracted around it, shrinking the distance it had to cross into something small enough to manage. A photon takes this to the far end. The muon's clock slows dramatically. The photon's clock stops entirely. A muon still ages, just slowly. A photon never ages at all. Scientists cannot directly observe the inside of a photon's experience. The math breaks down when you try, and we will get to that. But the pattern is clear and consistent across every particle physics experiment ever run. The closer something gets to the speed of light, the slower its time runs. A photon at the speed limit gets 0 time. What this means on a human scale is difficult to hold in your head. The photon that lit up the face of someone you love was born somewhere, traveled through space for some amount of real-world time, then hit your eye. To the photon, your face and its birthplace are simultaneous. The space between you and the star or lamp that made it does not exist for the photon. There is no gap. You are not separated from the light sources around you by distance. The photon sees you and its source as touching. And if that picture already feels strange, wait until you hear what happens to the space itself at the speed of light. Because space does not just slow down at the limit. Space collapses. Everything about a photon's strange relationship with time comes down to one number: 0. A photon has exactly 0 rest mass. Every other particle you have ever heard of has some mass. Electrons have mass. Neutrons have mass. Even neutrinos, the ghostly particles that pass through the entire Earth like it is barely there, have a tiny but measurable mass. A photon has none. Absolute 0. That single fact is the reason for everything. When physicists talk about mass, they are really talking about resistance to change. Mass is the property that makes things hard to push and hard to stop. A train has enormous mass, so it takes massive engines to get it moving and massive brakes to stop it. You have mass, so you feel the effort when you climb stairs or catch a fastball. Mass also does something more fundamental. As an object with mass accelerates, the energy you pour into it does not just speed it up. The math shows that it also makes the object effectively heavier. The faster it goes, the harder it becomes to push further. Double the speed, and the resistance grows. Push toward the speed of light, and the effective heaviness grows without limit. At 99% of the speed of light, it is already enormously difficult to push the object faster. At 99.9%, it is much worse. At 100%, the math says you would need infinite energy. Infinite energy. The whole universe is worth of power, and then more, just to move one particle with mass to the speed of light. A photon sidesteps this entirely. 0 mass means 0 resistance. There is nothing to make heavier, there is no energy barrier to overcome. A photon does not accelerate to the speed of light. The moment it is created, it is already there, instantaneously. This happens because a photon is born from a pure energy event. An electron in an atom drops from a high energy state to a low energy state. The difference in energy has to go somewhere. It becomes a photon, a ripple in the electromagnetic field, already moving at the maximum possible speed the moment it exists. There is no launch, no takeoff, no building of momentum. One instant the photon does not exist. The next, it is moving at 186,000 miles per second. Now, scientists tried for a long time to determine whether a photon might have a tiny, undetected mass. Even the smallest mass would change everything. It would mean the photon could not quite reach the full speed limit, that it would slow down slightly over cosmic distances. Physicists have run extremely precise experiments searching for this. They have measured photons arriving from distant galaxies and found zero variation in their speed across billions of years of travel. As far as every measurement ever taken can determine, the photon's mass is zero. This confirmation matters because if the photon had even a tiny mass, its clock would tick. Slowly, but it would tick. The photon would age just very, very slowly over its cosmic journey. Zero mass means the clock does not just slow, it stops. The two facts are inseparable, and understanding that connection is what makes the next part so hard to accept. Because at the speed of light, space itself stops existing as a barrier. Imagine pushing a shopping cart across an empty parking lot. Easy. Now imagine the cart starts getting heavier the faster it goes. You push harder. It speeds up, but now it weighs twice as much. You push harder still. It goes faster, but now it weighs 10 times as much. The faster it gets, the heavier it becomes, and the more force you need. Now imagine the cart kept getting heavier without limit. No matter how much force you applied, it would never quite reach the speed you were aiming for. The target speed keeps retreating as the cart gets heavier. You can get close, very close, but you can never actually arrive. This is exactly what happens to any particle with mass as it approaches the speed of light. The energy required does not grow steadily, it grows without ceiling. Scientists describe this with a curve that climbs toward vertical. At 10% of the speed of light, the extra energy needed is barely noticeable. At 90%, the particle is already effectively several times heavier than it started. At 99%, it takes enormous amounts of energy just to push it 1% faster. At 99.9%, it takes even more. The curve never levels off. It keeps climbing forever. To push any object with mass to exactly 100% of the speed of light would require an infinite amount of energy. Scientists phrase this carefully. Infinite energy is physically impossible in a finite universe. So the wall holds. Always, every object with even the smallest amount of mass is permanently locked out of the speed of light. This has been tested in particle accelerators. The Large Hadron Collider near Geneva, Switzerland, accelerates protons to within a fraction of 1% of the speed of light. Those protons become enormously more energetic, effectively thousands of times heavier than when they start. The machines pour in staggering amounts of power just to push them that last fraction of a percent toward the limit. And they never quite reach it. The proton stays on the wrong side of the wall, always. A photon was born on the right side of the wall. It never had to cross it. It started at the speed of light because it has no mass to weigh it down, no resistance to overcome, no energy barrier to clear. Now here is the piece that ties it all together. Because mass and time dilation are directly linked. An object with mass, no matter how little, will always have a clock that ticks at some rate above zero. It will always experience some passage of time. You can slow that clock dramatically by going fast. You can stretch its seconds into hours. But the clock keeps moving. Only at the exact speed of light does the clock reach zero. And only something with exactly zero mass can reach that speed. Photons are the only known particles that qualify. There are other massless particles predicted by physics, like the gluon that holds atomic nuclei together, and both move at the same speed for the same reason. But the photon is the one we interact with every day, the one that carries vision, warmth, and information across the universe. And the information it carries travels in a way that will genuinely stop you cold when you understand what space looks like from its point of view. You already know that speed slows time, but Einstein's equations revealed something just as strange happening to space. When an object moves faster, the distance ahead of it compresses. The road gets shorter. This is called length contraction, and it is completely real. Imagine you are in a spaceship heading toward a star that is 4 light years away. At your normal cruising speed, it is going to take decades, but as you speed up, something odd happens. The distance to the star starts shrinking. From inside the ship, the star is moving toward you faster than your speed alone would predict. The space between you is literally getting shorter. Push the ship to 90% of the speed of light. The distance that measures 4 light years from Earth now measures only about 1.7 light years from the ship. Same trip, different measurement of distance. Both measurements are correct for each observer. At 99% of the speed of light, the distance collapses further. 4 light years become less than half a light year. The closer you get to the speed limit, the more the space in front of you compresses. Speed and length contraction grow together, the same way time dilation grows. They are the same phenomenon seen from 2 different angles. Space-time is one fabric, and both time and space warp together as speed increases. Now push this to the absolute limit, 100% of the speed of light. At that speed, length contraction reaches its extreme. The distance ahead does not just shrink dramatically, it collapses to zero, completely. The entire physical distance between the starting point and the destination becomes nothing. The photon has no journey to make because from its reference point, no space separates the 2 locations. This is why, from the photon's perspective, the place it was born and the place it dies are not separated by any distance. The inside of a star and your eye are adjacent. They occupy the same moment and the same location in the photon's frame, even if you measure 40 light years between them. Think about the last sunset you watched. Photons left the surface of the sun 8 minutes ago from your perspective. They crossed 93 million miles of empty space. You saw them arrive as a warm orange glow on the horizon. But each of those photons experienced no crossing whatsoever. The sun's surface and your eye were, from the photon's internal accounting, the same point in space-time. No distance, no duration. One event. Length contraction and time dilation are not separate effects happening at the same time. They are 2 words for the same distortion in space-time. Time collapses, and so does space, for the same reason, at the same moment, reaching zero together at the speed of light. Scientists have confirmed length contraction indirectly through particle experiments. The muons that survive from the upper atmosphere do so because their internal time dilates and, equivalently, they measure the 60-mile trip through the atmosphere as far shorter than 60 miles. Both descriptions give the same answer. Both are true simultaneously. A photon takes that collapse to its absolute end. 0 time, 0 space, 1 moment, 1 point. But what does that physically look like? If a photon has no experience of space or time, what is left? What does the universe look like from inside that frozen, collapsed frame? This is where things leave familiar territory completely. Length contraction happens in the direction of travel. The space ahead of you shrinks as you speed up, but the space to your sides, above and below, stays the same. The distortion is directional. This means something strange at the extreme limit. If you could ride alongside a photon, the universe ahead of you would not just look closer, it would look compressed. Every galaxy, every star, every object lined up in the direction you were flying would get squished together. Their separations would shrink. They would appear to pile on top of each other in the forward direction. As you approach the speed of light, that compression intensifies. Stars that were spread across thousands of light years in the forward direction start appearing as if they are stacked almost on top of each other. The deeper you look in the direction of travel, the more compressed the universe becomes. At the exact speed of light, the compression reaches infinity. Every point in the universe ahead of you, from the nearest atom to the farthest galaxy at the observable edge of the cosmos, collapses into a single 2D plane. Everything collapses to zero thickness in the direction of travel. The three-dimensional universe, the same one you live in, flattens into a single sheet hanging directly in front of you. The entire depth of the cosmos, billions of light years of space, becomes a flat surface with zero thickness. Now think about what this means for the photon's experience. A photon travels in one direction. Space in that direction collapses. The distance between its birthplace and its destination becomes zero. The photon does not travel from one location to another. It simultaneously occupies both locations because from its accounting, they are the same location. The universe is a flat sheet, and the photon presses against both sides of that sheet at once. To an outside observer, the photon takes real time to cross real space. You can watch it travel. You can measure the 8 minutes it takes to cross from the Sun to Earth. The delay is real for you, but there is no delay from the photon's side. This is one of the genuinely weird parts of special relativity. Two observers can both be completely right about the same event and get completely different measurements of time and distance. The outside observer measures a journey of 93 million miles, taking 8 minutes. The photon's frame shows zero distance and zero time. Both are equally valid descriptions of the same physical event. Einstein called this relativity, and it was genuinely revolutionary. Before 1905, everyone assumed there was one true distance and one true time for any event, and all observers would agree. Einstein showed that distance and time are personal. They depend on who is measuring and how fast they are moving. The only things that stay the same for all observers are the speed of light and the space-time interval, a combined measurement of distance and time together. Everything else is observer-dependent. A photon exists at the extreme end of this. Its universe is literally flat. Its time is frozen. Its birth and death are the same event. And that last piece, being born and dying in the same instant, carries implications that get stranger the longer you sit with them. A photon from the Andromeda Galaxy takes 2.5 million years to reach Earth. You can look up at the night sky and see it arrive. It takes a moment that, from your perspective, is clearly happening right now after a journey that lasted longer than our species has existed. From the photon's perspective, it was born and absorbed simultaneously, not almost simultaneously. The same frozen instant. There is no contradiction here. Both descriptions are physically accurate. The 2.5 million years is real for you and every other observer with mass and a ticking clock. The 0 seconds is real for the photon. Space-time allows both to be true because time and distance are not absolute. They shift depending on the observer's motion. Here is the way to picture it without getting lost in the math. Imagine a photograph taken the exact moment a match is struck, and another photograph taken the exact moment that same match burns out an hour later. For you, those two photos represent an hour of time. But now, imagine a particle of light that was created when the match was struck and destroyed when the last ember hit the floor. For that particle, both photographs are the same photograph, identical moment. This is what it means for a photon to have no experience of time. Every event in its entire existence collapses to a single point. Scientists confirm this pattern through more than just atomic clocks and muon experiments. Researchers studying distant cosmic events have measured the behavior of particles moving at extreme speeds and found the time dilation matched Einstein's predictions precisely. The math holds. The photon's zero-time experience is not a speculation about something unmeasurable. It is the logical endpoint of a framework that has been confirmed at every level physicists have been able to test. And here is the piece that makes this more than just physics trivia. When you look at the night sky, every star you see is connected to your eye by a single photon. That photon does not care about the distance. It does not experience the journey. From its perspective, you and that star are touching. You are not separated by light years of empty space. You are adjacent to every light source you can see. Look up on a clear night. Every point of light is reaching you through a particle that perceives no gap between you. The universe, from the photon's view, has no distances. It is a flat, timeless, simultaneous thing. Now here is the question physicists keep circling back to. If a photon does not experience time or space, does it make any sense to say it has a perspective at all? Does it experience anything? Or is talking about a photon's point of view a category error, like asking what the color blue sounds like? The math breaks when you try to answer that formally, and the breakdown is stranger than you might expect. Something actually goes wrong inside the equations. Numbers that should represent reality instead produce results that mean nothing. Before we get there, though, we need to understand how human scientists actually proved that time bends, because the proof did not come from equations on a chalkboard. It came from flying clocks around the world on commercial airplanes. The first person to measure the speed of light did not have a laser, a clock accurate to a billionth of a second, or a physics lab. He had a telescope, a notebook, and a problem that would not stop nagging him. His name was Ole Rømer. He was a Danish astronomer working in Paris in 1676. His job was to track the moons of Jupiter, specifically a moon called Io, which orbits Jupiter quickly enough that it disappears behind the planet and reappears on a regular schedule. Rømer was building a precise table of these events so that sailors could use Io's movements as a kind of universal clock for navigation at sea. The problem was that Io kept running early or late. When Earth was on the close side of its orbit to Jupiter, Io emerged from behind the planet slightly ahead of schedule. When Earth was on the far side, Io appeared behind schedule. The difference across the whole year added up to about 22 minutes. Nobody could explain it. Rømer figured it out. The light carrying information about Io's position had to cross different amounts of space, depending on where Earth was in its orbit. When Earth was far from Jupiter, the light took longer to arrive. When Earth was close, the light arrived sooner. The delay was the time it took light to cross the extra distance. He used that delay and his knowledge of Earth's orbital size to estimate how fast light was traveling. His number came out to around 132,000 miles per second, about 30% slower than the true value. But the direction was exactly right, and the method was completely sound. For the first time in human history, someone had established that light has a finite speed. It moves fast, but it takes real time to cross real distances. Before Rømer, most scientists assumed light was either infinitely fast or so fast that measuring it was impossible. Rømer's discovery changed the question. Instead of asking whether light has a speed, scientists started asking how fast. Getting an accurate answer took another 2 centuries of increasingly precise experiments, but the conceptual breakthrough happened in Paris, in a notebook tracking the schedule of a distant moon. And Rømer's insight has a strange connection to what we now know about photons. He realized that information carried by light is always delayed. The Io he was watching was Io from the past, showing where the moon had been some minutes earlier. Every astronomical observation is a picture of the past, not the present. When you look at the sun, you see it as it was 8 minutes and 20 seconds ago. When you look at the nearest star beyond our solar system, you see it as it was 4 years ago. When astronomers point their telescopes at distant galaxies, they are seeing those galaxies as they existed millions or billions of years in the past. The universe, as seen from Earth, is entirely made of old light. We have never seen anything in the present. Every observation is history. But here is what Rømer could not have known. The photons carrying all of that old information experienced no delay. The ancient light from billions of years ago arrived without the photon ever knowing it took a long trip. The history belongs to us, the observers. The photon has no history at all. That gap between our experience and the photon's experience would not be formalized for another 229 years. It waited for a young man sitting in a patent office in Switzerland with a very specific question in his head. In 1887, 2 scientists set out to prove something that everyone believed was obviously true, and instead destroyed the entire foundation of classical physics. Their names were Albert Michelson and Edward Morley. They were based in Cleveland, Ohio. Their goal was to detect the medium through which light waves travel. Here is the logic they were working with. Waves need something to travel through. Sound waves travel through air. Ocean waves travel through water. Scientists in the 1800s assumed that light waves must also travel through something. They called this invisible substance the luminiferous ether. It was supposed to fill all of space, the medium that carried light from the sun to the Earth. If the ether existed, then Earth was moving through it as it orbited the sun, and that motion should create a measurable difference in the speed of light, depending on which direction you measured it. Light traveling against Earth's motion through the ether would fight a slight headwind and move slightly slower. Light traveling with Earth's motion would get a slight boost and move slightly faster. Michelson and Morley built an extremely sensitive device called an interferometer to detect this difference. It was a brilliant, careful experiment, and it found nothing. The speed of light was exactly the same in every direction, regardless of Earth's motion through space. No headwind, no tailwind, no difference at all. This result was so troubling that Michelson himself did not believe it at first. He ran the experiment again. Same result. Other scientists repeated it. Same result. The ether did not exist, and the speed of light was completely constant for all observers regardless of their motion. This was a crisis. If light always travels at the same speed for everyone, the math of the time simply could not hold. Speeds are supposed to add and subtract. If I throw a ball at 30 miles per hour from a train moving at 60 miles per hour, the ball travels at 90 miles per hour relative to the ground. Everyone agreed on this. Newton built it into his equations. It was foundational. Light refused to follow this rule. 18 years passed before Einstein resolved the contradiction. His answer was to take the Michelson-Morley result at face value and follow the logic wherever it led. If the speed of light is truly constant for all observers, then time itself must be flexible. Space itself must be flexible. The universe bends time and distance to keep the speed of light fixed. The ether was not the medium for light. Space-time was. And space-time is not a rigid, fixed backdrop. It is a dynamic, flexible fabric that stretches and curves depending on motion and gravity. Every modern understanding of the photon, its zero-time experience, its length contraction, its timeless journey, flows directly from what Michelson and Morley found in a basement in Ohio in 1887. They were trying to confirm something. They ended up shattering something. And the man who picked up the pieces built a theory so accurate that the whole world still depends on it every single day, in a way most people never think about. In 1971, two physicists named Joseph Hafele and Richard Keating did something that sounds ridiculous. They bought tickets on commercial passenger jets, brought extremely precise atomic clocks as carry-on luggage, flew around the world, and checked whether the clocks had changed. They had. The clocks that flew around the world were measurably out of sync with identical clocks that had stayed on the ground. The flying clocks had ticked fewer times, by exactly the amount Einstein's equations predicted. 6 decades after Einstein published his theory, two scientists with airplane tickets proved it was accurate enough to measure with clocks you could pack into overhead storage. An atomic clock keeps time by counting the vibrations of individual atoms, usually cesium atoms, which oscillate at a rate of over 9 billion times per second. They are accurate to within 1 second every 300 million years. Sensitive enough to detect the difference in time between a clock at sea level and a clock at the top of a tall building, because even that small difference in altitude creates a measurable gravity difference, which in turn changes the rate at which time passes. Hafele and Keating used this precision to catch the time dilation created by airplane speed. Commercial jets fly at around 500 miles per hour. That is nowhere near the speed of light. The effect is tiny, but tiny is not zero, and an atomic clock can detect tiny. When the planes landed, the flying clocks had ticked slightly slower than the ground clocks. the passengers had aged by a slightly smaller amount than the people who stayed home, by a fraction of a microsecond. Real, measured, confirmed. This experiment closed the argument for most scientists. Time dilation was not a mathematical curiosity or a philosophical abstraction. It was a physical effect, measurable with instruments you could carry onto a plane. The experiment also revealed something worth pausing on. Every person who has ever flown on an airplane has aged slightly less than they would have if they had stayed on the ground. The effect is too small for your body to notice, far less than a single heartbeat of difference. But it is real. The pilot who has logged 30 years of long-haul flights has aged slightly less than their identical twin who never left the ground. Time is genuinely personal. Your clock is not the same as another person's clock. The universe does not run on one shared time. It runs on billions of individual times, one for each observer, each ticking at a slightly different rate depending on that observer's speed and the gravity around them. For an observer moving at the speed of light, the difference is not slight, it is total. The clock stops. And now that we have seen the proof at human scales, with planes and atomic clocks, there is a more dramatic version of this happening every minute in the satellites above your head. Right now, over 20,000 miles above your head, dozens of satellites are orbiting Earth. Each one carries an atomic clock. Each one is broadcasting a precise time signal that your phone uses to figure out exactly where you are on Earth's surface, down to within about 10 feet. This system works because of triangulation. Your phone receives signals from multiple satellites and calculates its position based on the tiny differences in when each signal arrives. The math requires the satellite clocks and the ground-based clocks to be perfectly synchronized. Even a tiny drift in the timing would throw off the position calculation. Here is the problem. The satellites are moving at roughly 8,700 miles per hour. Because of that speed, their clocks run slow due to time dilation. They tick slightly slower than identical clocks on the ground. The effect is small but precise. The satellite clocks lose about 7 microseconds per day compared to ground clocks. At the same time, the satellites are far from Earth's surface, where gravity is weaker. Weaker gravity means space-time is less curved, and time actually runs slightly faster up there than at sea level. This effect adds about 45 microseconds per day to the satellite clocks, pushing them in the opposite direction. Together, the net result is that the satellite clocks run about 38 microseconds faster per day than they should compared to ground clocks. 38 microseconds sounds tiny, but the GPS system uses the speed of light for its calculations, and light covers roughly 7 miles in 1 microsecond. A 38 microsecond error would translate to a position error of more than 250 miles per day, every day. Compounding, within a week your GPS would tell you that you are in a completely different country. Engineers correct for this by programming the satellite clocks to run at a deliberately adjusted rate before launch, so that once they reach orbit and experience their actual time dilation, they end up ticking at the correct rate relative to Earth's surface. The correction is calculated directly from Einstein's equations. Every navigation system on the planet, every shipping route, every emergency response that uses GPS location, every app that tells you where to turn, runs on a correction factor derived from the theory of relativity. Einstein solved this in 1905. His math keeps your maps accurate in the present. This is not a historical curiosity. The moment engineers removed relativistic corrections from GPS satellite programming in an early test, the position errors grew to exactly the predicted amount within hours. Put the corrections back, and the accuracy returned. Time dilation is not abstract. It is woven into the infrastructure of modern life. Now take all of that and push it to the extreme case. The photon moving at the full speed of light. If 38 microseconds per day matters enough to break a navigation system, what does a total stop of time mean for what the photon experiences? It means the light that built the GPS system and the light that created the universe billions of years ago share one quality. For both of them, not a single second has passed. A photon's journey to your eye does not start at the sun's surface. It starts somewhere almost impossible to reach, deep in the core, under pressures and temperatures that would vaporize any material humans have ever created. The sun's core sits at a temperature of about 27 million degrees Fahrenheit. At that extreme, hydrogen atoms fuse together into helium, and the process releases enormous amounts of energy. That energy takes the form of high-energy photons, gamma rays, each carrying far more energy than the visible light photons that eventually reach Earth. The core is also incredibly dense, so dense that a photon cannot travel in a straight line for more than a fraction of an inch before it slams into another particle. It bounces, it scatters, it gets absorbed and re-emitted in a different direction. Then it bounces again, over and over, in what physicists call a random walk, moving in no consistent direction, just ricocheting through the dense plasma of the sun's interior. This journey from the core to the surface takes an enormously long time. Scientists estimate somewhere between 10,000 and 100,000 years, depending on the path. The photon is not traveling in a straight line. It is wandering, a drunkard's path, through a vast, hot, crowded interior. Over those thousands of years, the photon loses energy through each collision. It starts as a gamma ray. By the time it works its way to the surface, it has become a lower energy photon, much closer to visible light. The sun does not just produce light. It transforms high-energy radiation into the gentler wavelengths that reach your eye. And then, one day, the photon finally reaches the outermost layer of the sun. The density drops. No more particles close enough to cause another collision. The photon breaks free. It enters open space. At that moment, everything changes. The photon, which spent up to 100,000 years trapped in a crowded stellar interior, now faces open vacuum. It crosses the 93 million miles between the Sun and Earth in 8 minutes and 20 seconds, moving in a perfectly straight line at full speed. From outside, the timeline looks dramatic. 100,000 years of wandering, 8 minutes of freedom, then arrival. But from the photon's perspective, all of that, every collision in the solar core, every random scatter, every gradual loss of energy over tens of thousands of years, plus the 8-minute crossing of interplanetary space, happened in 0 seconds. The photon that smashes into a solar particle in the core and the photon that hits your eye are, from the photon's accounting, simultaneous events. 0 time spent trapped inside the most intense environment in the solar system. 0 time spent crossing 93 million miles of vacuum. All of it simultaneous, all of it the same instant. This fact makes something quietly strange about sunlight. Every photon that has ever warmed your skin or lit your room began its journey long before human civilization existed. The sun's light reaching you today started its random walk through the solar interior before the first human beings walked on Earth. It took thousands of years to claw its way out. Then, 8 more minutes to cross the solar system. And the photon experienced none of it. That timeless delivery from deep inside a star to the surface of your skin is about to get stranger. Because the oldest photons in existence are not the ones from our sun. They are from somewhere much further back. The moment a photon escapes the sun's surface, it enters the cleanest, emptiest road in the solar system. No atoms to bounce off. No plasma walls pressing in from every side. Just open vacuum stretching 93 million miles to a small blue planet orbiting at a comfortable distance from a medium-sized star. At 186,000 miles per second, that crossing takes 8 minutes and 20 seconds. To put that distance in perspective, if you drove a car at highway speed without stopping, day and night, the trip from the sun to Earth would take about 170 years. A passenger jet flying non-stop would need roughly 19 years. The fastest spacecraft humans have ever launched would take several months. A photon does it in the time it takes to make a bowl of pasta. But here is the thing most people miss about that 8-minute journey. The light reaching your eyes right now is showing you a sun that no longer looks exactly like that. You are seeing the sun as it was 8 minutes and 20 seconds ago. If the sun were to somehow vanish at this exact moment, you would not know for 8 minutes and 20 seconds. You would keep seeing it, feeling its warmth, watching light stream through your window. Then, 8 minutes later, it would go dark. The delay is built into reality. Light is fast, but the universe is big enough that even the fastest thing in existence takes real time to cross it. This delay shapes everything astronomers do. Every observation of anything beyond Earth is an observation of the past. The moon you see is the moon from about 1.25 seconds ago. Jupiter is anywhere from 32 to 52 minutes in the past, depending on where Earth sits in its orbit. The nearest star beyond our Sun is 4 years in the past. The Andromeda Galaxy is 2.5 million years in the past. Astronomers do not see the universe as it is. They see it as it was, layered across different depths of time. The further they look, the further back in time they see. Now pull the photon's perspective back into this. You are looking at a star 1,000 light years away. That star's light left 1,000 years ago from your perspective. To the photon carrying that light, the star's surface and your eye are the same location in space-time, the same frozen instant. The 1,000 years of travel is yours. The photon holds none of it. Everything you've ever seen in the night sky arrived through particles that never traveled at all, from the photon's point of view. The entire history of astronomical observation, every telescope ever built, every photograph of a distant galaxy, every discovery made by looking outward, all of it came from particles that experienced zero of the journey. The delay is our experience. The simultaneity is the photon's surface after 100,000 years of wandering still arrives at the same frozen moment it was born. Imagine what this means for photons that have been traveling not 8 minutes and not 1,000 years, but 13,800 million years. Those photons exist. They are hitting your skin right now. And they are the oldest things in the observable universe, carrying information from a time before any star, any planet, or any galaxy existed. About 13,800 million years ago, the universe was a dense, blindingly hot soup of energy and particles. There were no stars, no planets, no galaxies, no empty space to speak of. Everything that exists today was packed into a state so hot that atoms could not even form. Every time a proton and electron tried to combine into a hydrogen atom, the surrounding heat ripped them apart instantly. Light could not travel freely through this environment. The universe was opaque. Photons collided with free particles constantly, bouncing in every direction, trapped in a fog so thick that nothing could see through it. Then, roughly 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons could finally stick to protons. Atoms formed. Hydrogen filled the cosmos, and suddenly, for the first time, the universe became transparent. The photons that had been trapped in the fog were released. All at once, across the entire universe, light broke free and streamed outward in every direction. That moment of release sent a flood of photons into space that has been traveling ever since. Those photons are still here. They fill the universe right now, arriving from every direction at every moment. Scientists call them the cosmic microwave background. It is the oldest light in existence, the afterglow of the universe becoming transparent for the first time. From our perspective, those photons have been traveling for 13,800 million years. The universe has expanded enormously in that time, stretching the wavelength of those photons from visible light into microwave radiation. They are invisible to human eyes, but detectable with the right instruments. Satellites have mapped them across the entire sky, producing a detailed image of the infant universe as it looked 380,000 years after its beginning. That image shows slight temperature variations, regions where matter was slightly denser or slightly thinner. Those variations eventually grew into the structures we see today. The filaments of galaxies, the cosmic voids, the galaxy clusters, the seeds of everything that exists, were photographed in that ancient light. Now hold this alongside the photon's perspective. Every one of those ancient photons has experienced exactly 0 seconds since the moment it was released from the primordial fog. 0. The universe was 380,000 years old when those photons were freed. From their perspective, that release and the moment they hit a detector on a satellite orbiting Earth are the same instant. 13,800,000,000 years of cosmic history happened around them, during what the photon experienced as a single frozen moment. The oldest things in the observable universe have never aged. They carry the image of the universe's first light, and they hold it as if it just happened. Because for them, it did just happen. Scientists confirmed the existence of this ancient light in 1964, when 2 radio astronomers named Arno Penzias and Robert Wilson detected a persistent signal coming equally from every direction in the sky. At first, they thought it was interference from pigeon droppings in their antenna. It turned out to be the oldest light in the universe. The universe's first photons, carrying its oldest image, detected by 2 scientists who thought they had a pigeon problem. And if photons that old have never aged, the question becomes unavoidable. What does it mean for something to exist outside of time? Can a photon truly be said to experience anything at all? Einstein first asked this question as a teenager. What would you see if you could travel alongside a beam of light? He never fully answered it. And the more physicists have studied it, the clearer it becomes that the question might be unanswerable. But we can describe what the universe would look like from as close to that perspective as physics allows. Imagine you are in a spacecraft accelerating toward the speed of light. As your speed increases, something strange starts happening to the sky ahead of you. Stars that were spread across a wide arc of the sky begin to shift. They move toward the front of your view, clustering into a smaller and smaller circle directly ahead. This is called relativistic aberration, the bending of light's apparent direction caused by extreme speed. As you push faster, the circle shrinks. Stars from behind you appear to move to the front. The entire sky, every star in every direction, begins collapsing into a single point directly ahead of you. The universe is folding inward. At the same time, those stars change color. Stars ahead of you shift toward blue and violet as their light gets compressed into higher energy wavelengths. Stars to the sides take on a red tint. The whole sky pulses with color shifts that correspond to how fast you are moving. Push further toward the speed of light, and the circle of light ahead becomes blinding. Every photon in the observable universe is now arriving from that single forward direction, compressed and focused. The universe behind you appears completely dark. Everything is in front, piled into one impossibly bright point. At the exact speed of light, that point becomes infinite. The entire electromagnetic content of the observable universe, every photon from every source in every direction, collapses into a single, infinitely intense, dimensionless dot. Directly ahead, there is no depth, no left or right, no above or below, just a single point of infinite brightness, surrounded by absolute darkness. The three-dimensional universe has become a single point. This is the closest we can get to describing the photon's view. The universe it was born into is a flat, collapsed, dimensionless point. Every location it could possibly travel to is the same point. Its birthplace and its destination are indistinguishable. Space has completely lost its meaning. Physicists note carefully that this is a limit description, an extrapolation of what happens as speed approaches the maximum, not a true statement of what the photon experiences. The actual math breaks down before you reach that limit, for reasons we are coming to. A photon does not observe the universe from inside a valid reference frame, the way a person on a spaceship does. But the image captures something true. At the speed of light, space collapses. Distance stops being a property of reality. The universe, for something moving at that limit, has no spatial dimension in the direction of travel. One point, simultaneously everywhere the photon will ever be. Now, here is what makes this more than a visual exercise. Every color you can see is a photon arriving from a different energy level. The difference between red and blue, between a warm sunset and a cold winter sky, comes down to which part of the energy spectrum each photon carries. And the way photons carry that color has its own strange story. Close your eyes for a moment, now open them. Every color you see arrived in this room as a photon. The red of a stop sign, the blue of the sky, the yellow of a lamp, the green of a leaf. Every single color is the same kind of particle, a photon, carrying a different amount of energy. That energy difference is the only reason colors look different from each other. A red photon carries the least energy of all the colors in the visible spectrum. A violet photon carries the most. The other colors sit between them in a precise order: red, orange, yellow, green, blue, violet. Each step up that ladder is a step to a higher energy photon. The energy level of a photon determines its frequency, how fast its electromagnetic wave oscillates back and forth. A red photon oscillates at roughly 430 trillion times per second. A violet photon oscillates at around 750 trillion times per second. Your eye detects these frequencies and your brain interprets the difference as color. Below red, photons carry even less energy, and their frequency drops into infrared, which you feel as heat but cannot see. Your skin detects infrared photons from a warm stove without your eyes registering anything. Below that are microwaves, and below those are radio waves. All of them are photons, all moving at the same speed, all carrying different amounts of energy. Above violet, photons carry more energy than your eye can process. Ultraviolet photons give you sunburn. X-ray photons pass through soft tissue but get absorbed by dense bone. Gamma-ray photons carry so much energy that they can break apart the molecular structure of living cells. Every category of electromagnetic radiation you have ever heard of, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, is the same fundamental particle carrying different energy levels. They are all photons. They all travel at exactly the same speed. They are all timeless. A radio wave photon broadcast from a tower right now and a gamma-ray photon fired from a distant neutron star are identical in kind. They differ only in how much energy they carry. Both move at 186,000 miles per second. Both experience zero time. The sun emits photons across the full spectrum, but Earth's atmosphere filters most of them. Ozone absorbs ultraviolet photons, protecting living things from that high-energy radiation. The gases in the atmosphere absorb many infrared photons, holding heat near the surface. The visible range slips through cleanly, which is why your eyes evolved to detect exactly that range. Life on Earth shaped itself around which photons the atmosphere allows in. What lands on your eyes is a narrow slice of what the sun sends. An extremely specific energy window, selected by millions of years of atmospheric filtering, is what you call daylight. And all of it, every photon from every source, is a timeless particle born in an instant, racing across space without experiencing a single moment of that crossing, arriving in your eye and vanishing. The color of the world is the energy signature of particles that never aged. Now here is where the picture gets darker. Some photons never make it out. Gravity can trap them completely, and the place where that happens is one of the most extreme environments in the universe. Light moves at the fastest speed the universe allows. Nothing slows it down. Nothing pushes it sideways. In open space, it travels in a perfectly straight line, forever. So how does a black hole stop it? The answer is that a black hole does not slow the photon down. It bends the road the photon travels on. Everything in the universe follows the curves of space-time. Earth orbits the Sun because the Sun bends space-time around it, creating a curve that Earth follows. The deeper the curve, the stronger the gravitational pull. A black hole creates a curve so extreme that it bends all paths inward. Every possible direction, every road through space-time curves toward the center. A photon still travels in a straight line, but a straight line on a curved surface is different from a straight line on a flat surface. If space-time bends toward the black hole, the photon following its straight path follows the bend. It curves inward, and if the curve is sharp enough, inward is the only option left. There is a boundary around every black hole called the event horizon. Outside this boundary, light can still escape if it is moving away from the black hole at the right angle. Cross inside the event horizon, and the curvature of space-time becomes so extreme that all paths lead inward, straight ahead, sideways, even backward. Every direction points toward the center. A photon that crosses the event horizon has no geometrically valid path that leads outward. It follows its straight line, and that line leads inward. Always. This is why black holes are black. No light escapes. The photons that formed near a black hole and crossed that boundary are gone forever from the perspective of any outside observer. They continue on their path inward, but that path has no exit. Astronomers confirmed the existence of black holes through indirect evidence first: the motion of stars orbiting invisible massive objects, the behavior of gas swirling into compact regions. Then, in 2019, a global network of radio telescopes produced the first actual image of a black hole's shadow, a dark circle surrounded by glowing gas, exactly as Einstein's equations predicted. The image showed the event horizon of a black hole at the center of a galaxy, 55 million light-years away. The glowing ring around the shadow is light that came extremely close to the event horizon but escaped. Some of those photons looped almost all the way around the black hole before curving outward. Scientists call this a photon sphere, a region where photons travel in circular orbits. If you stood in the right spot near a black hole, you could theoretically look straight ahead and see the back of your own head, because light would have curved around and come back to your eyes. Now here is the strange connection back to time. Near the event horizon, where space-time curves most intensely, time slows dramatically for any object falling inward. From far away, an observer watching someone fall toward a black hole would see that person slow down, freeze at the horizon, and never quite cross it. The falling person, from their own experience, crosses and falls inward quickly. For a photon that gets captured, its timeless nature meets the most extreme space-time distortion in the universe, two extremes meeting. And what happens inside is something no information has ever escaped to tell us. Everything described so far treats the photon as a particle, a small thing moving along a definite path. But quantum mechanics, the science of the very small, says something completely different about what a photon actually does between the moment it is emitted and the moment it is absorbed. According to quantum mechanics, a photon does not travel along a single specific path. It travels along every possible path simultaneously. When a photon leaves a light source and heads toward a detector, it takes every route available to it at the same time. It goes the short way, it goes the long way around. It curves left, it curves right. It takes paths that loop backward. It takes paths through distant galaxies and back. All of these paths happen simultaneously, and the photon is on all of them at once. When the photon is finally detected, all those possibilities collapse into a single event. The photon is found at one location, but before detection, it was genuinely spread across all possible paths, and those paths interfere with each other like ripples on a pond, adding together in some places and cancelling out in others. That interference pattern is what determines where the photon is most likely to be detected. Scientists proved this with an experiment called the double slit. Fire a single photon at a barrier with two narrow slits cut into it. On the other side, place a screen that records where the photon lands. If the photon was simply a tiny ball, it would pass through one slit or the other and land in a spot directly behind one of them. But that is not what happens. Over many trials, single photons build up an interference pattern on the screen, alternating bands of light and dark, as if each individual photon interfered with itself by going through both slits at once. The photon acts like a wave spread across both slits simultaneously, producing the exact pattern you would get from two overlapping waves. The strangest part, if you place a detector at the slits to find out which slit the photon went through, the interference pattern disappears. Detecting the path collapses the photon back into a particle behavior. The act of measuring which way it went erases the wave behavior. The photon changes how it behaves depending on whether it is being observed. Now add the photon's zero-time experience to this picture. The photon takes every possible path simultaneously and experiences zero time during any of those paths. So from the photon's perspective, it simultaneously occupied every possible location it could ever reach, all in the same frozen instant. This is where special relativity and quantum mechanics stop talking to each other cleanly. Relativity describes a photon with a definite trajectory, a particle moving at the speed of light along a path through space-time. Quantum mechanics describes a photon as a spread-out probability cloud with no definite path until it is measured. Both descriptions are accurate in their own domains. Both produce predictions that match experiments with extraordinary precision, and yet they describe the same particle in fundamentally incompatible ways. Reconciling them is one of the biggest unsolved problems in physics, and right at the center of that problem, unavoidable and strange, sits the timeless photon. For about 300 years, scientists argued about what light actually is, and the answer turned out to be both at the same time, depending on how you look at it. In the 1600s, Isaac Newton argued that light is made of tiny particles he called corpuscles. He based this on the fact that light travels in straight lines and casts sharp shadows. Waves, he pointed out, bend around corners. Light does not. A century later, a physicist named Thomas Young performed the double-slit experiment and showed that light produces interference patterns, the alternating bright and dark bands that only waves create. Newton appeared to be wrong. Light was a wave. Then, in 1905, Einstein published a second revolutionary paper alongside his special relativity work. He showed that when light hits certain metals, it knocks electrons out of them in a way that only makes sense if light arrives in discrete packets of energy, not as a continuous wave. Each packet carries a fixed amount of energy, hit the metal with dim light of the right frequency, and you still knock electrons out. Hit it with bright light of the wrong frequency, and you knock out nothing. Waves do not behave this way, only particles do. Einstein called these packets quanta, and he showed that light is made of them. This is the photon. So Young showed light is a particle. Both experiments are repeatable, accurate, and correct. The resolution is that light is neither a classical wave nor a classical particle. It is something that does not have a clean name in everyday language. Physicists call it a quantum object. It follows rules that only make sense at the scale of atoms and smaller, rules that have no equivalent in the world of footballs and cars. When you set up an experiment to measure the wave properties of light, you get wave properties. When you set up an experiment to measure particle properties, the photon delivers whichever answer your experiment is designed to receive. This is called wave-particle duality, and it applies to everything at the quantum scale, not just photons. Electrons show the same behavior. Atoms do. Even molecules made of dozens of atoms have been observed interfering with themselves in double-slit experiments. The quantum world is built from objects that are fundamentally neither waves nor particles in the way those words are normally understood. For the photon specifically, this duality sits in strange tension with its timeless nature. As a wave, the photon is spread out through space, oscillating as it travels. As a particle, it is a single event, a discrete transfer of energy at a definite location. And as something moving at the speed of light, with zero time experience, it is simultaneously at every point it will ever occupy. All three descriptions contain truth. None of them alone contains the full picture. Physicists have learned to work with all three simultaneously, using whichever description makes correct predictions for the situation they are analyzing. This works. The predictions match experiments to extraordinary precision. But it leaves open a deeper question that the math does not answer cleanly. What is the photon actually doing when no one is measuring it? That question leads directly into the part of the physics that genuinely breaks. Here is where the story takes a turn that even professional physicists find genuinely unsettling. Special relativity gives us a way to calculate how any moving observer experiences time and space. You take the observer's speed, apply Einstein's equations, and calculate how their measurements differ from a stationary observer's measurements. This works for everything. Fast rockets, muons falling through the atmosphere, GPS satellites in orbit. But when you try to do this calculation for the photon itself, something goes wrong. Einstein's equations for calculating a moving observer's experience require you to divide by a factor called the Lorentz factor. This factor is based on how close the observer's speed is to the speed of light. For a rocket at 90% of the speed of light, the calculation is straightforward. For a rocket at 99%, the calculation still works, with a more extreme result. At 100% of the speed of light, the Lorentz factor requires division by zero. Division by zero does not produce a number. In mathematics, it is undefined. The equation breaks. It produces no answer. Not an infinite answer, but no answer at all. The mathematical framework that describes every other observer in the universe produces a complete breakdown when applied to the photon. This is not a gap that physicists expect to fill with better math. The breakdown is structural. Special relativity is built on the concept of a valid reference frame, a perspective from which measurements can be made. A valid reference frame requires an observer that can be at rest, that can stop moving and take measurements from a fixed point. A photon can never stop. It has no valid rest state, so by definition, it cannot have a valid reference frame in the language of special relativity. When physicists say the photon experiences no time, they are extrapolating from the pattern seen at speeds approaching the limit. As objects approach the speed of light, their time experience approaches zero. The natural extension of that pattern to the photon's speed is zero time. But this is an extrapolation, not a calculation. The calculation itself cannot be made. This matters because it draws a line around what we actually know versus what we are inferring. The time dilation pattern is confirmed at every measurable speed below the speed of light. The end point of that pattern, zero time at the speed of light, is the logical conclusion. But the photon's actual internal experience, if it has one, is genuinely inaccessible to the equations. Some physicists argue this means the question of the photon's experience is meaningless. If the math cannot reach it, there is nothing there to ask about. The photon has no perspective, because perspective requires a valid reference frame, and the photon lacks one. Others argue that the breakdown of the equations is the most interesting part. It might indicate that something deeper is happening at the speed of light, something that requires a more complete theory to describe, one that unifies relativity with quantum mechanics in a way that does not yet exist. That unification, if it ever arrives, would need to say something definitive about the most fundamental particle we interact with every single day. But there is another layer to this, because even the photon we have been describing, the particle, the wave, the timeless messenger, is itself a simplification of something stranger. The division by zero is not an accident. It is a signal. Throughout the history of physics, equations breaking at extreme conditions have pointed toward missing pieces in the underlying theory. When Newton's equations for gravity produced strange results near massive objects moving very fast, it pointed toward Einstein's relativity. When early quantum calculations produced infinitely wrong answers for electron energy levels, it pointed toward a deeper theory of quantum fields. The Lorentz factor reaching zero and triggering division by zero when applied to the photon's reference frame is another such signal. The equations are telling us that the conceptual framework being applied does not extend to this case. The photon sits at the boundary of where special relativity's description of observers and reference frames is valid. What exactly is at that boundary? Physicists have a few competing ideas, none of which are settled. One view holds that the concept of a reference frame simply does not apply to photons. A reference frame requires an observer with mass, capable of rest, capable of carrying a clock. A photon has no mass, can never rest, and carries no clock. Asking about the photon's reference frame is like asking what is north of the North Pole. The question sounds reasonable but points toward a location the coordinate system cannot describe. A second view treats the division by zero as a hint that space-time itself behaves differently at the exact speed of light. Perhaps the four-dimensional fabric of space-time undergoes a structural change at the limit. Perhaps the two-dimensional collapse that length contraction implies at the speed of light is a real geometric feature of space-time, not just an observer effect. Some physicists working on theories of quantum gravity explore whether space-time itself has a discrete structure at small scales, and whether the photon's behavior at the speed limit reveals something about that structure. A third view, taken seriously in some interpretations of quantum mechanics, holds that the photon does not have a journey in any meaningful sense. It is emitted at one event and absorbed at another, and the space between those events contains only probability. The photon does not travel through space. It transitions between two quantum events, and the path is a useful fiction for calculating where it is likely to go, not a physical track it actually follows. Each of these views produces correct predictions for observable behavior. None of them has been ruled out. Each one implies something different about what the photon actually is. The one thing all of these views agree on is that the photon is not a simple ball rolling through space. Whatever it is, it resists the kind of complete description we can give to almost everything else in the universe. It behaves like a particle when measured. It behaves like a wave when not. Its reference frame is undefined. Its internal experience is inaccessible. And yet it carries every bit of information we have ever received from the universe. Every image, every color, every beam of sunlight, every ancient star. All of it delivered by something our best equations cannot fully describe from the inside. And the deeper you dig into what the photon is made of, the stranger the answer gets. Forget the ball. Forget even the wave on a pond. The most accurate description physics currently has for a photon comes from a framework called quantum field theory. In this picture, the photon is not a tiny object moving through empty space. It is a vibration in a field. Picture the entire universe filled with an invisible, omnipresent fabric called the electromagnetic field. This field exists everywhere, at all times, even in the deepest vacuum of intergalactic space. It has a value at every point in the universe. Under normal conditions, those values are quiet, near zero, barely disturbed. When something energetic happens, like an electron losing energy as it drops to a lower state inside an atom, it disturbs the electromagnetic field at that location. The disturbance propagates outward through the field. That propagating disturbance is the photon. It is a ripple. A specific quantized ripple, one with a fixed packet of energy determined by its frequency, but a ripple nonetheless, spreading through the field rather than a ball flying through empty space. This picture explains several things the particle description struggles with. It explains how a photon can show wave interference with itself in the double-slit experiment. The ripple spreads through both slits simultaneously, the same way a water ripple passes through two gaps in a barrier at once. It explains how photons can be created and destroyed. Particles in the ordinary sense do not pop into and out of existence, but ripples in a field start and stop naturally. It explains why photons have no mass. The electromagnetic field has properties that make its excitations naturally massless. Quantum field theory is the most precisely tested theory in the history of science. Its predictions for the behavior of electrons and photons have been confirmed to better than 1 part in 1 billion in some experiments. Engineers use it to design the transistors in every computer chip on Earth. And yet, it does not resolve the photon's relationship with time. A ripple in the electromagnetic field still travels at the speed of light. The field itself permeates space-time. The ripple still obeys the same rules of time dilation and length contraction as any other photon description. The clock of the ripple, if you could define 1, still reads 0. What the field picture adds is a sense of scale and substance to the emptiness around us. The vacuum of space is not truly empty. It is full of fields at their ground state. The electromagnetic field plus the fields corresponding to every other particle fills all of space continuously. What we call empty space is a network of quiet fields waiting to be disturbed. A photon crossing the universe is a single note played on an instrument that fills the cosmos. And that field is not the only one. There are fields for electrons, for quarks, for the particles that carry the nuclear forces. All of them everywhere, all of them capable of producing ripples that interact with each other, create particles, destroy particles, and carry forces across the universe. Most of those interactions happen through a type of photon that barely counts as existing at all. Real photons carry light, they carry heat, they carry radio signals and X-rays and the image of every face you have ever seen. But there is another kind of photon that never travels anywhere, never gets detected, and exists for such a short time that it technically violates the rules of energy conservation while it lives. These are virtual photons, and they are responsible for one of the most important forces in the universe. When two electrons come close to each other, they repel. Negative charges push away from each other. Everyone learns this in middle school. But the question most textbooks skip over is what actually carries that repulsion across the space between the electrons. What is the messenger? The messenger is a virtual photon. One electron emits it, the other absorbs it. The exchange of that virtual photon is the mechanism of the electromagnetic force. Every repulsion between like charges, every attraction between opposite charges, every electrical interaction in chemistry, in biology, in every circuit ever built, happens through the continuous exchange of virtual photons. Virtual photons are real in the sense that they are required to make the calculations work. Quantum field theory uses them as the mathematical scaffolding that connects charged particles. Remove them from the equations, and the predictions collapse. But virtual photons violate a rule that real photons follow. Real photons always carry exactly as much energy as their frequency demands, and they can never be detected directly carrying the wrong amount. Virtual photons can momentarily carry energy values that would be impossible for a real photon. The universe allows this for a brief time because of a principle in quantum mechanics that permits energy to be borrowed, so to speak, for intervals short enough that the imbalance cannot be measured. The shorter the time, the larger the allowed energy imbalance. Virtual photons mediating forces over very short distances can carry enormous energies. Virtual photons mediating forces over large distances carry tiny energies. This is why the electromagnetic force weakens with distance. And the strangest part, virtual photons do not travel at the speed of light. They do not need to. They are not constrained by the same rules as real photons because they never escape into the open world, where those rules can be checked. They are internal scaffolding, existing only for the duration of the interaction they mediate. This means virtual photons do not share the timeless property of real photons. They live for a defined interval, do their job, and vanish. They have a beginning and an end that are genuinely separate events. Time, in a limited sense, the same particle, real or virtual, follows completely different rules depending on whether it is observable. This is one of the deepest peculiarities of quantum field theory. The photon you can detect operates under one set of constraints. The photon you can never detect operates under another. What this tells us about the nature of the photon and about time itself is something physicists are still actively working through. But there is one implication of all of this that almost no one stops to consider. Every image you have ever seen, every face, every landscape, every moment of visual experience you have ever had arrived through particles that experience none of it. Right now, trillions of photons are hitting your eyes every second. Each one carries energy. Each one oscillates at a specific frequency that your eye's receptor cells detect. Each one transfers its energy to a molecule in your retina called retinal, which changes shape when it absorbs a photon. That shape change triggers a nerve signal. That signal travels to your brain. Your brain interprets the pattern of signals as an image. The entire visual world you experience, every color, every shape, every moving object, every face you recognize, is built from a stream of energy transfers by timeless particles. The photon that showed you the expression on someone's face this morning was born somewhere. A lamp, the sun, a screen, and traveled to your eye without experiencing any time. It transferred its energy, reshaped a molecule in your retina, and ceased to exist. The image you built from it, the recognition you felt, the memory you stored, those belong entirely to you. The photon carried the information and felt none of it. This is not metaphor. It is a direct physical description of how vision works. Your entire experience of the visual world is constructed from timeless messengers that deliver information they have never held on to. Now, take this further. Every memory you have that involves sight entered your brain through photons. Every movie you have watched, every book you have read, every face you have ever seen, all of it came through particles that experienced zero time, zero distance, zero journey. Neuroscientists studying vision describe the brain not as a passive receiver, but as an active constructor. Your brain takes the sparse stream of photon-triggered signals and builds a rich, detailed model of the world. Most of what you see is prediction. Your brain fills in gaps, corrects for eye movements, smooths over blind spots, and presents you with a coherent picture assembled from fragmentary data. The rich, continuous visual world you feel yourself inhabiting is a mental model built from the energy transfers of timeless particles. The gap between the photon's experience of delivering information and your experience of receiving it is vast. The photon experienced nothing. And here is the question that sits at the edge of all of this, one that physicists and philosophers have both circled for over a century. If a photon experiences no time, carries information across the universe, and delivers it to an observer, who then builds experience from it, where does time actually live? Is time a feature of the universe itself, or is it something that only emerges when an observer with mass, with a ticking clock, with continuity and memory, is present to experience it? The photon does not know, the math does not say, and the answer might be closer to you than you expect. Look up at a clear night sky, pick any star, it does not matter which one. That star is sending photons toward you right now. Some of those photons will miss the Earth entirely. Some will enter the atmosphere and scatter. A tiny fraction will make it all the way to your eye. When one does, it completes something remarkable. The photon that hits your eye was created by a nuclear reaction inside that star. It was born from energy released when hydrogen atoms fused together under enormous pressure and temperature. It escaped the star's interior, crossed the open space between you and that star, entered your eye, and delivered its energy to a cell in your retina. From your perspective, there is an enormous distance between you and that star, possibly dozens, hundreds, or thousands of light years. The light took a long time to cross that space. From the photon's perspective, there is no distance. The star's interior and your retina are adjacent. They are not separated by space or time. The fusion event that created the photon and the moment it hit your eye are one single frozen instant. The space between you is zero. You and that star are connected right now through a particle that perceives no separation between you. When a photon from a distant star reaches your eye, the star and your body are, from the photon's accounting, touching. This is confirmed physics. Length contraction at the speed of light collapses all distance in the direction of travel to zero. The photon has no journey. Its start and end are the same event. What this means on a human level is difficult to hold. The night sky does not show you distant objects. It shows you sources of timeless particles that are, from the only valid reference point that exists at the speed of light, directly adjacent to you. The universe is full of distances from our perspective. From the photon's perspective, there are no distances. Every source of light you can see, the sun, the moon reflecting sunlight, artificial lights in your city, the stars, distant galaxies, is connected to your eye right now through particles that see no gap between those sources and you. The scale of the universe that astronomers measure in light years, billions of them in every direction, is real from our perspective, and it is zero from the photon's perspective. Both are true simultaneously. Now here is the question this raises that physicists have not resolved. If the photon perceives no time and no distance, and if every observation of the universe we have ever made came through photons, what does that mean about whether time and space are fundamental properties of reality or properties of the observer? Is the universe truly ancient and vast? Or is ancient and vast only the story that observers with mass and ticking clocks tell about information delivered by timeless particles? String theorists, loop quantum gravity researchers, and physicists working on the foundations of quantum mechanics are all in different ways grappling with this question. And their early answers point towards something even the most optimistic physicist finds strange. Time might not be a fundamental property of the universe. It might be something that emerges from deeper structures that are themselves timeless. And if that is true, the photon is not an exception to how the universe works. It might be showing us how the universe actually works at its most fundamental level. The photon has no time. That much is clear. But physicists are now seriously asking whether time is fundamental at all, or whether it is something that only appears to exist because of how observers with mass experience the world. This is a genuine open debate in theoretical physics, not a philosophical sideline. Some of the most respected researchers in the field have argued, based on the mathematics of quantum gravity, that time does not appear in the deepest equations describing the universe. The most striking version of this argument comes from an equation called the Wheeler-DeWitt equation, developed in the 1960s. This equation attempts to combine quantum mechanics with general relativity to describe the entire universe as a quantum system. The result is striking. Time does not appear in the equation. The universe described by this equation has no variable for time. It exists in a kind of eternal, static state. If that equation is on the right track, then time as we experience it, the feeling of moments passing, of past and future, is something that emerges at larger scales when complex systems of particles interact with each other. Time is what clocks measure, and clocks are complex physical objects made of many particles. At the level of individual particles, time may not be a fundamental feature of reality. A photon, moving at the speed of light with a frozen clock, might not be violating the normal rules of time. It might be showing us what reality looks like without the emergent layer that we call time. It might be operating at the level where the deeper, timeless structure of the universe is visible. This idea connects to something called the block universe view of space-time, which Einstein's equations naturally support. In the block universe picture, all moments of time, past, present, and future, exist simultaneously as a four-dimensional structure. There is no flow. There is no moving present moment. There is just the four-dimensional block, and the experience of time flowing is what happens when a conscious observer with a ticking clock moves through a slice of that block. A photon with a frozen clock does not move through the block. It exists as a single line in the block, connecting two events, its creation and its absorption, with no separation between them. This view of time is unsettling because it implies that the future already exists. Every moment you will ever live is already part of the four-dimensional structure. Your sense of moving forward through time is a perspective effect, not a fundamental feature of what is happening. Most physicists treat this as a philosophical consequence of the math rather than a physical claim about consciousness and experience. But the math is the math. And the math says the photon is not doing something unusual by living outside of time. The math says the photon might simply be living closer to what the universe fundamentally is. That possibility sits at the edge of current physics, where the next generation of discoveries is most likely to happen. And those discoveries are coming fast. A photon carries information. It carries it at the maximum possible speed without losing it, without aging, without distortion, across any distance the universe contains. Scientists are now building technologies that exploit this to do things that seemed impossible just 20 years ago. Quantum computing uses individual photons to carry units of quantum information called qubits. Unlike a classical computer bit, which is either 0 or 1, a qubit can exist in a superposition of both states simultaneously, the same wave-particle duality that makes the double-slit experiment so strange. A photon traveling every possible path at once carries more information in a single state than a classical bit ever can. Quantum computers using photonic systems are already performing specific calculations faster than any classical computer ever built. The field is advancing rapidly, with research teams around the world racing to build photonic quantum computers capable of solving problems that would take traditional computers longer than the age of the universe. Quantum communication uses single photons to transmit encrypted information with a security that is physically guaranteed. When two particles are quantum entangled, measuring one instantly determines the state of the other, regardless of the distance between them. Photons are the ideal carriers for this kind of entanglement. Any attempt to intercept the photon destroys its quantum state and alerts the receiver that the message has been tampered with. Eavesdropping becomes physically impossible. China has already demonstrated quantum key distribution over satellite links spanning thousands of miles, using entangled photons. Europe and the United States have active programs building quantum communication networks. The next decade will likely see the first practical quantum internet links, transmitting information with security that no computing power can break. Beyond communication and computing, physicists are using ultra-precise photon measurements to probe the boundary between quantum mechanics and gravity. Experiments using single photons in carefully controlled gravitational fields are testing whether the two great theories of physics behave consistently at their interface. The results will either confirm current theories or reveal the cracks that point towards something deeper. And researchers studying the cosmic microwave background, those ancient photons from the Big Bang, are building increasingly sensitive detectors to map their polarization patterns in finer and finer detail. Those patterns carry information about the first fraction of a second after the Big Bang, before atoms existed, when the universe was a dense quantum soup. Reading those patterns is like reading a message sent from the earliest moment the universe could send messages. The photon that took 100,000 years to escape the sun and 8 minutes to reach your eye is the same fundamental particle that physicists are now using to build the quantum internet, the quantum computer, and the telescope that looks back to the dawn of time. A particle with no mass, no age, and no journey is turning out to be one of the most useful objects in the universe. But all of this technology, all of this discovery, rests on one fact that sits quietly underneath everything. Every discovery in this story comes back to the same particle, a speck with no mass, no age, no experience of distance, born instantly at the maximum speed the universe allows, destroyed the moment it delivers its energy. carrying between those two events everything the universe has ever communicated. The photon is the messenger the universe uses for everything. Forces between charged particles, virtual photons, information crossing cosmic distances, real photons, the warmth on your skin, infrared photons from the sun, the image in your eye, visible light photons. The signal your phone uses to locate itself, radio frequency photons bounced off GPS satellites whose clocks are corrected for time dilation. The universe built its communication system out of particles that experience none of it. The ancient light of the Big Bang is still traveling. Every second, photons from the moment the universe first became transparent are hitting Earth, hitting you, delivering their energy and dissolving. Each one was present at the most dramatic event in the history of everything. Each one experienced that event, and your body is the same frozen instant. The nuclear fires of distant stars are sending photons toward Earth right now. Some of those stars no longer exist. They burned out long ago, but their light is still traveling, still arriving, still delivering the energy of fires that went cold before humans appeared. The star is gone, the photon is here. And from the photon side of things, the star's fire and your eye are simultaneous. Every color you have ever seen came from a timeless particle. Every photograph ever taken was made by trapping the energy of ageless messengers. Every telescope ever pointed at the sky collected particles that experienced no distance, no journey, no time at all. Physics spent centuries asking what light is. The answer is still not complete. The photon behaves like a wave and a particle. Its reference frame is mathematically undefined. Its internal experience cannot be calculated. Virtual versions of it carry forces without existing long enough to be detected. Its energy level is the only reason colors look different from each other, and it never ages. The universe is 13,800,000,000 years old. The photons created at its beginning are still here, carrying its oldest image, experiencing that age as a single frozen moment. They have been in transit for the entire history of the cosmos and have experienced none of it. They are as new as the moment they were born. Every image you have ever seen, every ray of sunlight that has ever warmed your face, every star you have ever looked at on a clear night, arrived on the back of a particle that exists outside of time. You live inside a universe of enormous age and incomprehensible scale. You experience it through particles that find it small and instantaneous. The universe is vast. The photon makes it a single moment. And somewhere out there, right now, a star is releasing a photon that will take thousands of years to reach a human eye. For that photon, the star and the eye are already touching.